So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Toshihiro Yada, who will tell us about non-Haar random circuits form unitary designs as fast as Haar random circuits. So Toshihiro is a PhD student at the University of Tokyo, and he's working in quantum information and quantum thermodynamics. His research interests include randomness generation and the emergence of chaotic phenomena in quantum many-body systems. And he has also worked on thermodynamics under iterative quantum feedback. So Toshihiro, the floor is yours.
Okay, thank you for a kind introduction. And my name is Toshihiro Yada, from a PhD student from University of Tokyo. And today I will going to talk about our recent work on Haar random circuit forming unitary design as fast as corresponding Haar random circuit. So the collaborators of this work are Ryotaro Suzuki in Free University of Berlin, Yosuke Mitsuhashi in Riken, and Nobuyuki Yoshioka in New Tokyo. And the details of this work is in this paper, so if you are interested, please also refer to this paper. Okay. So sorry, can you hear me?
I think you muted yourself for a while, but I can hear you
Okay.
now.
Yeah. Sorry. So then I will start from the beginning. So sorry, I'm not
No,
used
I think
to
like we
use
heard the introduction, but when you changed to the next slide, you suddenly disappeared. Yeah.
okay.
Yeah, so you can go here at the outline.
Okay,
Yeah, it's
from
fine.
the outline slide. Okay, thank
Yeah.
you. So I actually usually use Zoom, and it's first time to use Teams. So
Oh yeah.
yeah.
Don't worry about it.
Okay.
Yeah.
Okay. So this is the outline of today's talk. So I will first introduce the background of this work, and then I will briefly summarize our main results and discuss their implications. And after that, I will go into the more detailed description of our results. Okay, and please feel free to interrupt me at any time if you have any questions or comments. Okay. So, so first I will start from the background part. So the randomness in quantum system has played a significant role both in the field of quantum information science and many-body physics. So it has various applications in quantum information processing tasks, such as the randomized benchmarking, randomized measurement, and random circuit sampling. Also, it lays a foundation for understanding the chaotic phenomena of quantum memory systems, for example, the information scrambling and summarization in memory systems. Okay. So the important notion to quantify such randomness in quantum system is the unitary T-design. The unitary T-design is the ensemble of unitary operations which reproduces the T's moment of the uniform distribution. So this figure illustrates the uniform distribution, or the Howe distribution of a unitary operation, which covers arbitrary unitary with the same probability. On the other hand, since the unitary T-design only concerns the T's moment of ensemble, it can even be a discrete set of unitaries, as shown in this figure. The T's moment of a unitary ensemble is completely characterized with the T's moment operator, which is defined as shown here and shown in this diagram. And so we say that a certain ensemble is an exact unitary T-design if this moment operator completely coincides with that of the Howe measure. And we say that a certain ensemble is an approximate T-design if the moment operator is sufficiently close to that of the Howe measure, okay, as shown in this inequality. Okay. So to better understand this notion of unitary T design, I will first introduce the basic implications of unitary 1 design and 2 design. So when a certain ensemble is an exact unitary 1 design, then it implies that the averaged expectation value of any observable coincides with that of the Haar random average, as shown in this equality. So this is because the averaged value of the unitary ensemble is complete. So the average value of the observable is completely characterized with the first moment of ensemble, as shown in this diagram. Also, we can say that if a certain ensemble is an exact unitary 2 design, then the variance of the arbitrary observable coincides with that of the Haar random average. Okay. So this variance of the observable is characterized with the first moment and second moment, as shown in this diagram. So therefore, we can say that we at least need a 2 design property to show the correspondence of the variance of observable, while we only need a 1 design property to show the correspondence for the expectation value. So as can be seen from these examples, the unitary T design with a larger T implies the stronger randomness in some sense. Okay. So in the previous works, it has intensively investigated how to create a unitary design on a many-body system. And the one of the most basic method to form unitary design on many-body system is to use the random circuit, where each local unitary gate are chosen from random ensemble. So here, I will consider the random circuit on n-qubit system, where each local unitary gates are chosen from How measure on the 2-qubit unitaries. So in such situation, it is easy to show that if we take a circuit depth sufficiently large, then the random circuit eventually forms unitary T design. For example, in the infinite depth limit. So, however, the question is how much circuit depth is required to form a unitary T design? And actually, in the previous works, it has already shown that the circuit depth of Poirier T is sufficient to form unitary T design on n-qubit system. So such analytical upper bound has been provided in various circuit structures, which is shown in this slide. So for example, in this 1D local circuit, we randomly choose one of the neighboring 2-qubit pair and apply the unitary gate on that pair in each layer. Okay. And in this O2O circuit, we randomly choose a 2-qubit pair from complete graph and apply unitary gate on that pair. Okay. So we call these types of circuit single layer connected circuit since the available gate in a single layer forms a connected graph covering all sides. Okay. On the other hand, there are the circuit structure which are not single layer connected, which we call the multi-layer connected circuit. So for example, the 1D brickwork circuit is multi-layer connected circuit since it does not form a connected graph covering all sides in a single layer, and we need at least need 2 layers for all sides to be connected. And in this for fixed architecture circuit, we need 3 layers to form a connected graph covering all sides. Okay. So in these various circuit structures, the T-design formation depth has been comprehensively investigated, which is summarized in this table. So for example, in the 1D local circuit, we need the circuit depth of n squared t, and in the 1D brickwork circuit, we need the circuit depth of nt. Okay. So I would like to comment that so in the 1D local circuit, we can only apply a single unitary gate on each layer, while in 1D brickwork circuit, we can apply an n/2 gate in a single layer. So the total number of required random gates are the same in 1D local and 1D brickwork circuit up to a constant factor. Okay, and we can see that in all of these circuit structures, the circuit depth of Poirier T is sufficient to form T design on encoded system. Also, I would like to comment on this patchwork circuit, which is a special circuit structure proposed in the last year. By utilizing this circuit structure, we can form unitary design on log n depths, which is much more efficient compared to other circuit structures. So I will discuss the details of this circuit structure later in the last part of this talk. So anyway, as summarized here, the T-design formation depth is intensively investigated for various circuit structures in recent previous works. So, however, in these previous theoretical works, they mainly focused on the situation where each local unitary gate are chosen from Haar measure, uniform distribution of local unitary ensemble. And they do not consider the situation where each local gate are chosen non-Haar randomly, for example, from a discrete gate set. So on the other hand, in the practical experiment, each local unitary gate are chosen from non-Haar measure due to the restrictions in implementation or the inevitable noise, such as the coherent error. So therefore, the natural question arises is to what extent the unitary design formation rate is affected by the choice of local unitary ensembles. Okay. So actually, this is our main research question, and we provide a very simple answer to this question. So this is the answer to the question, and we analytically proved that the general non-Haar random circuit form unitary T design that's fast as the corresponding Haar random circuit up to a polylog T factors. So this is actually the very short summary of our results and the take-home message of our result. So we consider the general non-Haar random circuit where each local gates are chosen from general non-Haar randomness. And in such situation, the circuit depth required to form T design can be upper bounded with the L times C. And this L is the circuit depth required to form T design on the corresponding Haar random circuit with the same structure. And this C is the constant prefactor with respect to the system size, and also can be upper bounded with the polylog T term, where T is the moment order. So actually, the inverse of this C characterizes the strength of the local randomness, and therefore, if randomness of local ensemble is very weak, then this C can be very large constant. However, it's the constant with respect to n and can be upper bounded with polylog T. So it is always the same. So the scaling of the formation depth is not different from the corresponding Haar random circuit. Okay. So we prove such analytical upper bound for various circuit structures as summarized in this table. Okay. So as shown in this table, so our work provides the upper bound for various circuit structures, including multi-layer connected circuit and patchwork circuit, while the previous work focuses on the single-layer connected circuit. Also, our work provides the optimal upper bound up to a polylog T factor, while the previous work has a additional poly n factor, which is very large when the system size is very large. So this is the brief summary of our main results. And before going into the more detailed description, I will first introduce the applications of our results. So first, in terms of the practical application, our work enhances the flexibility of random circuit construction by relaxing the choice of local randomness without drastically changing the required circuit depths for generating global randomness. So it is widely known that the formation of unitary T design with shallow circuit depths is important for various uh, quantum information processing tasks such as randomized benchmarking and random circuit sampling. So our work guarantees that the cost for such tasks are not very different, even if we choose each local unitary gate uh, from a discrete gate set, for example. And also, our work has the implications to the many-body physics. So in the recent previous works, random circuit is often used as a tractable model of a quantum many-body system and the chaotic phenomena in these systems. Therefore, our work implies that in such random circuit models, the various chaotic phenomena related to the unitary design emerges universally at the same circuit depth order, independent of the choice of local randomness. So the examples of such chaotic phenomena include circuit complexity growth, information scrambling, summarization, and the decoupling of initial correlation and anti-concentration. Okay. So these are the main applications and implications of our results. And next, I will go into a more detailed description of our results. Okay. So for that purpose, I will first introduce the notion of the spectral gap, which is defined as shown here. So this m nu t is a moment operator for the t moment, and this spectral gap is called the t spectral gap. And it is widely known that this spectral gap quantifies the rate of unitary design formation. To be more specific, it is known that L-time convolution, L-time iteration of unitary ensemble nu forms epsilon approximate T design if L is greater than this expression. Since this expression includes the inverse of the spectral gap, we can say that it quantifies the rate of T design formation. Therefore, the goal of our work is to lower bound this spectral gap or the rate of T design formation in non-Haar random circuit. So if we can lower bound this spectral gap, then we can upper bound the required circuit depths. And the precise description of our first main result for a single layer connected circuit is shown in this inequality, where the spectral gap for non-Haar random circuit is lower bounded with the corresponding Haar random circuit. Okay. And this delta log term, orange delta log term, is a constant prefactor, and this is a local spectral gap defined as shown here. Okay. And this delta mu ij is a spectral gap for local unitary ensemble on ith and j skewed. And we take the minimization over all tutored pairs available in a single layer. So for example, in this 1D local circuit example, we take the minimization over these four local unitary ensemble. And this delta log term is defined as the minimum value of these local ensembles. Okay. So as can be seen from this definition, this delta log term does not explicitly depend on the system size n. And also from the previous work, we can show that it is lower bounded with inverse polylog t term if each local unitary ensemble contains a universal gate set. So in the following, I will briefly describe the proof sketch for this inequality. in a 1D local circuit, which is the simplest example of single layer connected circuit. So in the 1D local circuit, the moment operator for single layer is defined as shown here. So this mu LRT is the moment operator for single layer of 1D local circuit, and it is defined as the sum of each local unitary ensemble, since we randomly apply a local unitary gate for it in each layer. And this MII plus 1 is the moment operator for local unitary ensemble with general non-Haar measure. And also this M nu LLH term is the moment operator for corresponding Haar random circuit. And this PII plus 1 is the local moment operator for Haar measure on a calculated unitary. Okay. And in this setup, our goal is to lower bound the spectral gap for non-Haar random circuit, which is defined as shown here. So this empty Haar means the moment operator for the Haar measure on a entire system, global system. And so actually in the previous work, there is an established method to lower bound the spectral gap for Haar random circuit by mapping this moment operator to the frustration-free Hamiltonian and lower bound the energy gap for that Hamiltonian. So however, that established method is not directly applicable to this case, since this moment operator for non-Haar random circuit can even be a non-Hermitian, since each local ensemble is not Haar measure. Okay. Therefore, we need to consider another proof strategy, and we try to upper bound this term with the Gram matrix of the moment operator, which is the symmetrization of the moment operator. And by upper bounding this term, we try to upper bound the spectral gap for non-Haar random circuit. Okay. So for that purpose, I will first derive the operator inequality, which upper bounds the Gram matrix of the non-Haar random circuit with the moment operator for Haar random circuit. So here I will omit the superscript t for simplicity. Okay. So for that purpose, I will upper bound this term with the Cauchy with this expression where we use the Cauchy-Schwarz inequality. And next, I will upper bound each so this local term with the corresponding Haar measure as shown here. So here, small g term is defined as 1 minus local spectral gap. And by rearranging these terms, we can obtain this expression, which means that the Gram matrix of the moment operator is upper bounded with the corresponding the moment operator for corresponding Haar random circuit. And by applying the operator norm on both sides of this inequality, we can obtain the this inequality, which upper bound 1 minus delta nu LR squared with the corresponding Haar, with the spectral gap for corresponding Haar random circuit. And by a simple algebraic manipulation of this inequality, we obtain the desired inequality, which is our first main result. Okay. So while I here only show the proof sketch for a 1D local circuit, the similar proof strategy also applies to a general single layer connected circuit, for example, all-to-all circuit or circuit with general connectivity. Okay. So this is a proof sketch of our first main result. And actually, the similar results holds for the multi-layer connected circuit, which is our second main result. So this inequality is our second main result for a multi-layer connected circuit with architecture A. So this delta nu A is a spectral graph for the non-Haar random circuit with architecture A, and it is lower bounded with this term. So here, so this delta rock is a spectral gap is a local spectral gap which is defined in the similar way as the single layer connected circuit case. And this L is the connection depth of the circuit structure. And in this case, the connection depth is L equal 4, since we need 4 layers for all sides to be connected. And this LBA term is the best known lower bound for the corresponding for the spectral gap for corresponding Haar random circuit, which is derived in this previous work. And it is known that this lower bound is optimal up to a constant prefactor. And also in the case of 1D brickwork circuit, this lower bound coincides with the spectral gap itself, which means that our lower bound is sufficiently tight up to a constant prefactor. Okay. So this is the actually the second main result, and I do not go into the detailed proof for this inequality since it's more complicated compared to the single layer connected circuit. Okay. So this is our second main result, and finally I will discuss our results for patchwork circuit. The patchwork circuit is a circuit structure where the small patch of epsilon over n approximate T designs are glued together, as shown in this figure. Okay, so in these previous works, it was shown that in such circuit structure, epsilon approximate unitary T design on the entire encoded system is can be formed, and each small part can be composed over 1D brickwork Haar random circuit with a circuit depth of order log n. Okay, therefore, it means that by utilizing this patchwork circuit structure, we can create a unitary design with log n depths for n side system. So by combining these previous results with our results shown in the previous slide, we can immediately show that each small patch can also be replaced with non-Haar random circuit, and the required circuit depths can be upper bounded with a constant factor, constant multiple of the corresponding Haar random circuit. And this means that even with a non-Haar local randomizer, we can form a unitary design on encoded system with the circuit depths of order log n by utilizing this patchwork circuit structure. Okay. So this is our results for patchwork circuit. Okay. So finally, I would like to summarize our work. So we show that for general non-Haar random circuit, the T-design formation depth is upper bounded with polylog T factor times the formation depth for corresponding Haar random circuit, as shown in this figure. Okay, and this result implies a flexible unitary design formation for various applications, and also it implies the emergence of chaotic phenomena in the same circuit depth order in the random circuit models. Okay, so that's all for my talk. Okay, thank you for listening.
Thank you very much for very clear and very okay. So I guess you kind of finished quite early. We have plenty of time for questions
Yeah,
and discussion.
sorry.
Yeah, it's fine. Yeah, it's okay. Yeah. So if you have questions, please feel free to unmute yourself and ask them now. There's no particular question. Okay, maybe I can sort of ask one quick question first. So I think like so at least in my head, like the summary of the result is as you say here. So whenever you go from some T design where you're using locally, you're using Haar random, and now you're doing some non-Haar random thing. So you only pay like polylog T,
Yeah.
sort of like penalty for that. Like so
Yes.
is I can safely think of this in general, or is there some particular circuit structure where this doesn't quite hold?
So at least for circuit structure summarized in this table,
Mm.
so okay, so for example, so the very natural circuit structure, at least this as how random circuit property holds. So for various circuit structure. So what we show is so this as Har property is very general for comprehensive circuit structure. So I think yeah, in most cases this property is satisfied. Maybe we can create a special situation where such circuit such as Har property does not hold, but yeah, at least so for circuit structure investigated in the previous work with Har random circuit, we show that uh, we can form T design in the same circuit depth order. Yeah.
Mm-hmm. Right. Yeah.
So following up this question, I have a question about the effect of a connectivity in this upper bound. So it seems that now the circuit architecture for all kind of circuit architecture, you can derive this and upper bound. But how about if we have a different connectivity? Does it affect?
Okay, so the circuit depths, like, so your question is the dependence of on the formation depths. So dependence of the formation depths on the connectivity of the circuit. Right? So sorry, maybe I couldn't catch the
Maybe I
meaning
didn't.
of the question.
Maybe I didn't formulate my question properly. So in the last slide, 22 pages, you have showed a very general, very concrete result of this formation depths for non-Haar random circuit.
Yeah.
And somehow you have also derived this bound for different type of architecture of the circuit, right?
Yes. So we show this property for various circuit structure.
Yeah, and I'm just curious about does the connectivity of the device will affect your results, the analysis?
Yes. So okay. So actually, so our results are this inequality for multi-layer connected circuit and this inequality for single layer connected circuit. So it's more so for example in this one deal so for example in this single layer connected circuit result the dependence on the local unitary ensemble only appears in this as a this constant factor, and it does not depend on the connectivity of the circuit structure. So, but the spectral gap itself, so for example, the spectral gap for the Haar random circuit can depend on the circuit structure. So this inequality is satisfied for all single layer connected circuit, such as a 1D local circuit, 1D brickwork circuit. So 1D local circuit and O2O circuit. So for both of these circuit structure, so this inequality is satisfied. And in these 1D local circuit and 1D O2O circuit, this term, so the spectral gap for Haar random circuit is in general different. So the dependence of the structure appears in this term. So, and dependence of the local neutral ensemble appears in this term. So this is the contribution from the structure of the circuit, and this is a contribution from the local randomness.
Okay.
Yeah.
Okay. See.
Thank you for the question.
Thank you. So this data logs actually quantify the kind of Haar randomness of your local gate.
Yes. So this delta log characterizes okay. So this delta log characterizes the strengths of local randomness, and it's greater than it's greater than 0 and smaller than 1. So it is always satisfied, and yeah. So yeah.
Okay, thank you.
All right. So, have other people have questions?
Can I just check? So if for example we had something that was like, say, not quite Haar random, but maybe like a random Hermitian matrix that's like exponentiated with a small angle theta. So it's like kind of, you know, when you overlay lots of these, then you get something Haar random, but there's very low entanglement because theta is very small. Then I guess this constant here would be very small. And is that what would be happening in this situation?
Yes. So yeah. So in such situation, so if a local randomness is very in such situation, the local randomness is very small, and then in that case, so this delta log term is close to 0. And if this delta log is exactly 0, then this inequality becomes trivial. But if it's non-zero, then so yeah, it lower bound the rate of t-design formation depths, the rate of t-design formation, and yeah. So as you said, in that situation, this prefactor is very small, and it means that this prefactor appears here. This C term is very large, so it means the required circuit depth is very large. And however, so the important thing is, so this delta log does not depend on the system size and does not depend, so it is lower bounded with inverse polylog t term. So the scaling is the same even in that situation.
Yeah. And so one more question, which I guess maybe is not actually directly related to your research, but maybe, you know, because it's related to your research, but it's not a focus of your research. If we consider like some kind of T design that's like based on a finite gate set for the small terms, you could imagine building the bigger circuit where rather than sampling each block independently from the finite set, you could imagine introducing some correlations between blocks.
Yeah.
Are you aware of any results along these lines where they still show high randomness, provided the correlations are bounded or something?
So you mean that the situation where each local unitary gates are not chosen independently, but there is a correlation between the different gates? Yeah, I don't think there are much investigation on that direction. Yeah, the one reason is that the analysis is more simple if we choose in each local gates independently. And another reason is it is expected if we choose a random gate. So if we increase the randomness, so then the required gate is more. So the required circuit depth is more small. So it's just a naive intuition, but so for example, if we there is a correlation between these two layers, then the kind of randomness is becomes small. So randomness is decreased. So so rather than that such situation in a naive expectation, so so the circuit depth required is more small in the situation where each local gates are chosen independently. Yeah, I don't know, but maybe that direction is also important. Yeah.
No, I just wanted to like clarify. So when you make it correlated, is it like there's correlations across layers or just within the layer? Let's say if I have a brickwork, then I choose local unitaries. Like if I imagine if there are correlations within the layer, but not across the layers, this is still pretty good. Maybe.
Yeah. So So maybe such situation is tractable maybe because we can use so this lemma. So so this is iteration of the unit cell. So maybe it's not so within our theorem, but maybe it's applicable. So it can be extended to such situation. But if there is a correlation between the layers, then I think it's beyond what we show and what the previous work has shown. Yeah, but maybe the direction is also important because in the practical experiments they want to decrease the number of the number of random local gates. So since they want to decrease the change of the circuit structure, circuit construction. So yeah, maybe that direction is also important.
Okay, thank you.
Right. Yeah, okay, I guess I just want to see if anyone else wanted to ask questions. I actually have like one question, like just for concreteness. So for example, if I consider this brickwork, right? So now I guess like, for example, if those local unitaries I pick from Clifford's, then this kind of like your result can tell me explicitly what is the formation depth, right?
Yeah,
I can
and
yeah,
that's true. So sorry. So okay, so if we choose each local unitary gate from a Clifford gate, then so it is known that the Clifford circuit forms a unitary 3 design, but does not form unitary 4 design, actually. So, and our result, so for example, this inequality means that if the t is smaller is the same as the smaller than 3, then it means so this inequality is not trivial because this delta log term is greater than 0 for in such situation. But if the t is greater than 4, then this inequality becomes trivial because this delta log t term is 0 in such situation. So yeah, actually, so I didn't tell explicitly, but so in this general non-Haar random circuit, we assume that each local unitary ensemble contains a universal gate set. So in such situation, the T design is formed for a very large T, so exponentially large T with respect to system size. But so in the Clifford gate, so in the Clifford circuit, each local unitary gate does not include a universal gate set. So it means that the T design is not formed even if we take infinite circuit depths. Yeah. So, but still, even in such situation, this inequality still holds. And yeah, but yeah, for T greater than 4 case, it's trivial. Yeah.
Yeah.
So
Okay.
yeah.
I understand.